So, log functions, there are going to be certain things about the characteristics of a log function that we need to just know and have memorized. Because one thing that becomes really important as you move on up into higher level maths is that you need to be able to recognize, like when you're looking at a function, you need to be able to get a mental picture of what this is going to look like. So if you see a square, you know it's going to be a quadratic, and you can tell if it's open and up or if it's open and down. Whenever you see, an exponential, you can tell if it's going to be growth or if it's going to be decay, and those sort of things. So with logs, we need to know some of that same stuff so that when we see it, we can kind of get like a picture in our minds of what that graph would look like. So on Thursday, I think, we did look, maybe it was Friday for you guys, we did look in the notes about how the log is just a reflection over the line y equals x for the exponential, because those are inverses of each other. So, if you flip this back over, we would just have like an exponential growth formula. So one thing we can kind of think about is like how those two relate. So a log function of the general form, f of x equals a log base b of x, where b is greater than 0, and a and b are constants. A cannot equal 0 because if it equals 0, the whole thing equals 0. B cannot equal 1 because a log base 1 doesn't do anything, because 1 to any power always equals 1. So for this function, if a is greater than 0, then this is what the graph is going to look like. This is the big one that you have to have memorized. And for this, let's draw this in here, or highlight it. For this, you are going to have a vertical asymptote at the y-axis. Okay, so your domain for a log function is just from 0 to infinity, unless it has been shifted left or right, because you have a vertical asymptote here. This means, this is important, right here, you cannot take the log of 0 or a negative value. So if you see, if they're trying to get you to do log base 3 of negative 2, that would be undefined. Okay, you cannot take the log of a negative value or of 0 for that. And the reason is because if I think about trying to do like log base 3 of 0, right? If I make that equal to x and I rewrite it as an exponential, that'd be 3 to the power here and 3 to the power here. 0 equals 3 to the x. What power could you raise this to that would be 0? You might initially think 0, right? But what is 3 to the 0 power? It is 1. And if we try to use negative numbers, like 3 to the negative 2, that's not 0 either, or a negative number. It's going to be 1 over 3 squared. It's going to be 1/9. So this graph gets closer and closer and closer and closer to 0, but it never actually touches 0. We cannot do log of 0, right? So those are really important things for us to remember for logarithmic functions. Now the range is unrestricted. It's negative infinity to positive infinity for this. So this picture right here, this first one, is the one you really need to have memorized, because that would just be the basic log function. What is different about the second graph that they give you here? A is less than 0, which would mean that you have a negative number out in front of your log. And what does a negative out front do to your graph? Reflects it over the x-axis, right? So if A is less than 0, then it's reflected over the x-axis. Notice that you still, on this graph, have a vertical asymptote at the y-axis. The only way to move that vertical asymptote is to shift this graph left or right. If you shift the graph left or right, it's going to move the vertical asymptote with it. But if you don't shift it left or right, then your vertical asymptote will be at 0. Okay? Much like our exponentials, because these are just reflections of the exponentials, these graphs are either always increasing or always decreasing. They do not have any relative maximum or minimum points. They are also always concave up or always concave down. You're not going to have any points of inflection on a log graph. Now, when it comes to end behavior, things are going to be a little bit different for end behavior. Because if I look at this graph right here, if I look at my left statement, right, so far, every problem we've done on the left statement, we have said the limit as x approaches negative infinity of f of x. But does this graph approach negative infinity? Where do its x values stop? 0. So for logs, let's see, how shall I, this is everything else. For everything else, on the left side you do this. For logs, unless it's been reflected over the line, over the y-axis, usually its left is going to be the limit as x approaches 0, and it has to be from the left, from the right-hand side, because you do not approach 0 from the left-hand side on this of f of x. Now, that number for 0 can change if your graph has been shifted left or right, because if your graph has been shifted left or right, then you are going to have a different vertical asymptote. So that 0 is whatever your vertical asymptote is. It's a plus, showing us that it's from the right side. If f of x is like a log, any type of log function. Yeah.
So why is that 0 plus sign?
The plus sign behind the 0 tells us if we're going to from the left side or the right side. So if you don't have that little plus sign behind it, then you're approaching from both sides for every number except for infinity, because you can only approach infinity from one side. Like you can't actually get to the other side of infinity, right? So so you don't have to put it with an infinity because it's generally understood. But with a 0, you would be approaching from the left side or from the right side. So since this graph only exists on the right side of that graph, you are, like, as you go to the left side, you're approaching 0 from the right, because this graph is only on the right side of that line. So for this one, like, let's just do this graph that we're looking at here. The limit as x approaches 0 from the right of f of x would be what's happening. Remember, limits are always what's happening to your y value. So as you approach from the left, from the right, what is happening to your y values here? They're going down. So negative infinity would be your answer on the left side. If I do limit as x approaches positive infinity, because the right side does go to positive infinity of f of x, what do you guys think for that one? Okay, it is positive infinity. It feels a little bit like that has a horizontal asymptote, right? It's like it's not going up fast, right? It's growing slowly there. But logs are inverses of your exponentials. So exponentials, think about what they look like. Exponential growth, as it takes off, like on the right side, that goes up really, really, really fast, right? So when you flip it, it's still increasing, but just not as quickly. So you should always get positive or negative infinity for these. It can be a little confusing when you look at one on Desmos, because Desmos, like if I type in y equals log base 3 of x right here, I can see vertical asymptote here. Like if I zoom out, like it's going right next to that line right there. But if I zoom in really close to that point, I might pick the point too far away. Oh, how close can I get? Well, I think I'm about there. No. I picked the number too high. It's going to take too long. Let's say like right there at -6. It looks like it touches the graph, but if you get zoomed in close enough, it's not actually touching, right? For that, it would do the same on at that -27 as well. I just picked the number that I would have to zoom forever, and you might reach the limits of Desmos where it just says I can't zoom in anymore for that. But like for example, right here, it kind of looks like maybe this is getting closer and closer to a number 2. It kind of looks like a horizontal asymptote. And if you zoom out, it like starts to look even more like a horizontal asymptote. Like it looks like it's about 4 or 5 right there or something. But logs have vertical asymptotes. They do not have horizontal asymptotes. Because like if I think it is 5, right? Oh, y equals 5. If I think it is 5 right there, that looks pretty much like an asymptote. But if I zoom out like far enough, you're going to see it actually does cross that line. It will give you like a gray dot right there. Zooming in to see it exactly is probably going to be hard, but let's try anyway. I can't get zoomed that close, but it does actually cross right there. So logs only have vertical asymptotes. They do not have horizontal asymptotes. Exponentials only have horizontal asymptotes. They do not have vertical asymptotes for that. But sometimes if you're looking at it on Desmos, it might look like they do for that. So let's look at limit statements for these. So they kind of help us out a little bit on A right here. They say the limit as x approaches 0 from the right. That is our right limit statement. Alejandro, whenever I'm looking at that there, what are my y values doing as I go to the left side? Very good. It'll be negative infinity for that. On the right side, that's where our x approaches positive infinity, so we'd get the limit as x approaches positive infinity of f of x. And Alyssa, on the right side, what is happening to our graph there? Perfect. Approaching positive infinity. Okay, pretty much the graph we just looked at. All right, B is more like that second graph, right? It's been flipped upside down. So for this one, Mason, what would we say for our limit statement on the left for B right there? Okay. And what will we get for our answer there? Very good. Positive infinity, because as you go to the left, those y values are going up. Okay. Connor, what would the statement be on the right? Right. Okay. And pretty much you should only get positive and negative infinities here. And they should be opposite. So you should never have like positive infinity, or you should never have negative and negative. If you get positive infinity for one of them, the answer for the other is negative infinity. That should always happen with logs. The only time it will not be is if you have something that's been reflected over the y-axis. So if you were to see something like log of negative x right there, that would reflect the graph over the y-axis, and so it would change your limits it would actually be the left side would approach negative infinity and the right side would approach 0 for that. So the only time it will not be positive infinity is if this has been flipped over the y-axis for that. All right, for C, we need to think about what that graph is going to look like. So in this case, if we have a log with a positive number up here, then that is just our basic shape that we've had already, really like A, right? It has not been reflected. It doesn't even matter what the base is. That is going to change like how steep it is, but it's not going to change the shape. If you like zoom out on any of these, they're going to look the same. So for this, we would have the limit as x approaches 0 from the right of g of x, and that would be negative infinity, and then our limit as x approaches positive infinity of g of x would be positive infinity. Any questions? Mm-hmm. Yes. Yep. And if A is less than 0, then it would be one that's decreasing. Okay. Answer those next 3 on your own. Okay. Let's see. Michaela, what'd you get for A? Perfect. Concave up, decreasing on that one. Okay. Let's see. Molly Adams, how about B? Very good. Concave down, increasing. Okay. C was the most difficult because it did not give you the picture. Hank, what did you guys get? Concave up and decreasing. Yes. What would C look like? It looks like A, pretty much, right? Because it would be flipped upside down. So it would look like A for that. Okay. Now, let's look at some table stuff with this. And this would be kind of easy-ish to be able to fill in if you had the calculator, because you could do like a regression and figure it out. But I believe that they would probably have you doing this without a calculator in this case. So let's look at what's happening here. That tells us selected values of the several logarithmic functions are shown in the tables below. For each table, find the value of the constant k. So we need to remind ourselves what happens in a logarithmic table, because a logarithmic table is different than really any of the other tables that we have looked at. On most tables, we're looking for the x values to increase by a constant amount. What's different about the logs? What are we looking for in the logs? Y values are going up by equal amounts, and I heard somebody over here say multiply, and what were you talking about? The x values are being multiplied by a number. So the first thing we want to check here is to make sure that our y values are in fact going up. Oh, this is one of those ones where it does crazy stuff. All right, so these are in fact going up by 1 over here. What's happening to our x values? Times 2. So 1 times 2 is 2. 2 times 2 is 4. That's what we should have right there to fill in. K is going to be 4. And then 4 times 2 is 8. 8 times 2 is 16. That'll fill in our pattern. Okay, so try the others. Okay, if they're a little bit tougher, try those others. All right, so let's see, Chandler, what did you get for that second table there, the g of x table? K equals 2. And how did you decide that k should equal 2? Okay, so you're multiplying by 3, and to go backwards, you just need to divide by 3. So that looks good. And it's perfectly fine to do this. I didn't write it down, but this is okay because you're going up by 5 each time. Because we do always want to confirm that your y values are increasing or decreasing at a constant rate. Okay, so I saw lots of you with a 2 right here. Like we were doing okay on that, right? Then I saw a lot of blanks on the next 2, but I did see some of the correct answers. Okay, so looking at this one here, we can in fact confirm that this goes down 10, down 10, down 10, down 10. So we do have a constant rate on our y's, so we can look at the x's. We're looking for those. We're kind of looking for them to be multiplied, but are they being multiplied? So we've got like 4 to 5, 5 to 7. Like this is not working out. What do you think, Molly? Okay, that would be plus 4, and then from 11 to 19 would be plus 8. That's an exponential pattern. What has happened, logarithmic pattern, right? I guess it's kind of exponential for the x's there. Because what's happening here is this graph has been shifted up or down, so the pattern is not obvious, right? So like on the other 2, on the first 2, we could just see, oh yeah, I'm multiplying by 2. Or I'm multiplying by 3. Like you can just see the number that you're multiplying by. But on this one, this is a graph that has been shifted up or down a certain amount. So it's not showing that pattern quite so obviously. So if you look at your differences, that will help. Okay. Going to the last one. What do you guys think on the last one? Okay, that's right. E to the 4th is right. And this one, let me write down, this is 11 right here. Okay, how'd you get it?
We did like the second one of E of 1, even though there's nothing there. So that's like plus 3, and then E of 1 plus 3 is E of 2.
Okay, now, and so what you're looking at is you're looking at the exponents being added. Is that logarithmic? Like, because for exponential, you're supposed to multiply. Okay, it would be y, but it's not supposed to be, because they're exponents. So what you're really doing is you're like multiplying by e to the 3rd. Because if I do e to the negative 2 times e to the 3rd, then that adds my exponents together, and I'll get e to the 1st. And then I can do e to the 1st times e to the 3rd, and that's going to give me e to the 4th. So it's, your exponents are just being added by 3, which works out for this pattern. The actual value of that is being multiplied by e to the 3rd for that. So that works out. So that one's a little bit tricky. Okay, questions? All right, let's go on to that last part right there. Okay, and this is really where it matters that we know what the original looks like and that we remember what all those transformations do to a graph, right? So the original log function looks like this. It has a vertical asymptote at y equals 0. This is y equals log x, and the domain is 0 to infinity, and the range is negative infinity to infinity. Now, the good news about logs is that that range should not change, because if you flip it upside down, if you move it up, down, left, right, it's still going to go negative infinity to positive infinity. In order to make that range not negative infinity to positive infinity, you would have to do something like square the insides or something, which is not one of the transformations they're going to ask you about. So we could, looking at these functions, go ahead and just put negative infinity to infinity on all of these. So that's something to memorize. Like all log functions should have a range of negative infinity to infinity. That goes along with your end behavior, because your end behavior, you should always get positive and negative infinity, and they should be going opposite directions, which means your range should be negative infinity to infinity. So that requires very little thinking, but domain requires much more thinking, right? So, so if the range is always the same, the domain will stay the same unless we do some sort of transformation that changes our x. So if we shift this graph up or down, is it going to affect our domain? It will not, right? That only affects y values. If we stretch it out vertically or squish it down vertically, is that going to affect our x values? It will not. But if I shift it left or right, that's going to change my domain. Actually, just the horizontal compression or expansion does not change it, because this number is 0 right here, and when you multiply by 0 by anything, it just stays itself. So really, it's only shifts left or right that are going to change that domain. Yeah, in the parentheses. So like if I look at A, I do have a vertical expansion by a factor of 2. Does that change my domain at all? It does not. So 0 to infinity. Go with the classic domain there. Now, B has a negative 5 and an x minus 3 on the inside. Okay, what does that negative 5 do? It's going to reflect it. It'll also stretch it, right? Is flipping it upside down going to change the x values? It does not. It will change in behavior. If they were asking us about that, then we would care, right? But we don't really care about that. All we really care about is the shift to the left or to the right. So is this shifted left or right? That is going to be right 3. So we just take our domain and we're adding 3 to both numbers. 0 plus 3, of course, is just going to give us 3. Infinity plus 3 is still infinity, so 3 to infinity there. No, it should not. The only time it would change is if it's been reflected over the y-axis. Then it would be like negative infinity up to. But it should always have an infinity with it.
When would you change?
If I'll give you an example here next. I'll add one in so you can see that. Let's look at C. C is a little bit tricky because does the 8 on the outside matter for our domain? It does not. So we can kind of ignore it. It's going to make it like taller and skinnier, but it doesn't change our domain. It's that 2x plus 3 that will change our domain. So, the expansion or compression does not change your domain, but it does have to be considered whenever you're talking about what's going on right here, because this does not move to the left 3. Okay, whenever I don't know that any of us have asked you to look at horizontal expansions and compressions at the same time as shifts left and right yet, but whenever you're shifting something left and right, like if I have y equals a log of bx plus c plus d, that sort of has to be factored out front. So right here, this 2 affects what's happening with that 3, because we would do the compression first, which would change that 3 from being a left 3 to being different. I think the easiest way to do one like this, if it's not just a straight left or right, if it just is like B, we just know it's right 3, add 3. I think the easiest thing to do right here is I know that I can only take the log of a positive number, right? How do I write that algebraically? Something, if I've got, what's on the inside here? 2x plus 3. And I want to say that that's always positive. How could I write that? Greater than 0. Right? So whatever is inside of your log has to be greater than 0, because you cannot take the log of 0 or a negative number. So then I can just solve this simple little inequality here. 2x is greater than negative 3, and I could divide by 2. And so x is greater than or equal to negative 3 halves. So my domain is going to be negative, oh, I'm sorry. I added an or equal to at the very end for no reason, because it should not be there. I didn't include it on my original. So we got negative 3 halves to infinity. Okay. So if you have like a compression and a shift left or right, it's best just to set that greater than 0 and figure out what you have there. Now let's answer this question real quick. Like let's add in another one right here. Let's say I've got k of x equals 2 log base 4 of negative x plus 1 plus 7. Okay. Does the 2 or the 7, do those affect our domain? They do not. It's still going that affects range, and our range is already going to be negative infinity to infinity. So when I have this negative x plus 1 on the inside, that is affecting my domain. And it is a reflection over the y-axis, and it's actually going to be to the right one and to the right one instead of left one, because you sort of have to factor out that negative. It's kind of weird. But again, I think the easiest way to do this is take negative x plus 1 and say that it has to be greater than 0. Whatever is inside of that log has to be greater than 0. Yep. Yes, always greater than, it starts off as greater than 0. Now, on this one, we're going to see it flip from being greater than in this case, because the first thing we would need to do is we're going to subtract 1. And so we got negative x greater than negative 1. What do I have to do now? I've got to divide by negative 1. And when I divide by a negative on an inequality, I've got to flip the sign. So I've got x is less than positive 1. So my domain for this one would be all of the numbers less than 1. So the domain for this one would be negative infinity up to positive 1 for that. And range, of course, would still be negative infinity to infinity. Okay, that does have, like, the combination of reflections with shifts left and right get a little difficult to think about. So I just always set it greater than 0, and it takes care of itself as long as you don't forget to flip signs and stuff. All right, so